I welcome Professor Saraswati Madam from Usmania University, Mechanical Engineering Department. Madam will talk on nano finishing by magnetorheological fluid. I request Srividya to introduce Professor Saraswathamma Madam.
Good morning, ma'am. Before starting the session, let's have a brief intro of Professor K. Saraswathamma Madam. Madam has received her ME from Usmania University in 2001 and PhD in 2015 from Indian Institute of Technology, Delhi. After her post-graduation, she joined as assistant professor in the Department of Mechanical Engineering in the year 2001, and eventually she became a professor in the year 2017. Her research interests are in the areas of conventional and unconventional machining, magnetorheological fluid, applications of finite element technique, etc. She has published nearly 25 papers in peer-reviewed international journals in addition of 18 presentations in national and international conferences. She has guided 94 ME and several BE students. She is also a reviewer of international journals such as International Journal of Precision Engineering and Manufacturing, Materials Today Proceedings, Journal of Process Mechanical Engineering, etc. We are glad to welcome you, ma'am.
Thank you, Srividya. Thank you, Srividya, for nice introduction.
A very warm welcome, madam.
Welcome.
Thank you, madam. Thank you very much. And I'll start the share the screen.
Yes, ma'am.
Now I am able to, right?
We can see your screen, madam.
Then I'll keep it in the full screen mode. So a very good afternoon to all of you. Like almost we are near reaching to the 12 p.m. So good afternoon to all. And I'm just today my talk is on nano finishing using metallurgical fluid. First, I'll talk about more on this metallurgical fluid. What is metallurgical fluid is going to be. And then we'll go for this. My PhD is on nano finishing using metallurgical fluid. So that I'll touch upon finally. Right. So these are the outlines of my today's topic. First, we'll go for MR fluids, and then what are the devices that are based on this MR fluids are going to be. And next, we are going for the metallurgical finishing, and mainly how to characterize this metallurgical finishing fluid for applications of metallurgical finishing. And then finally, I'll go for the summarize this things. Before going for metallurgical, just 1 minute, please. So my net is not coming properly, please. So these MR fluids are generally smart fluids. These are the kinds of designated design materials where their properties can be controllable with application of external stimuli, which is generally sometimes we may apply this magnetic fluid or otherwise electrical fluid, field or otherwise stress or otherwise and heat. So, and these materials, their electrical properties are generally changes are controllable by external, applying this magnetic field. So in those generally we call as a metallurgical fluids. Right. So these are generally actively these metallurgical actively used in for engineering applications like include like fluids of foams, grease, elastomers, and plastomers. In the last 2 decades, if you see, metallurgical materials have gained great attention for the researchers significantly because of their silent controllable properties, and then potential applications are there to various fields like when you go for automotive industry, civil environment, and as well as military sector. Even generally, a few of them are generally in the biomedical sector also. As well as we are also can go for nano finishing applications also. So based on this, I'll go for just what is a metallurgical fluid is going to be. So where the electrical property can be able to vary with respect to this magnetic field application. So that generally these will form like a liquid to they'll change into a solid state. So means nothing but these metallurgical fluids are generally derived based on this rheos and then rheology. Rheo means nothing but in the Greek word, it is generally in English translation, if you see, that is going to be a flow. So rheology means nothing but a science of material flow under this load conditions, if you see. And this metallurgical fluids mean nothing but the fluids whose properties can be, that rheology can be, we can say viscosity increases with the application of the magnetic field. Once the magnetic field is generally going to be removed, then again it will come back to the original state, which is generally going to be a kind of a Newtonian fluid, like generally we can say little bit viscous is going to be there. So when you say this metallurgical fluids means the liquids that harden or otherwise they change their shape when they are applied this magnetic field. So this metallurgical fluids belongs to this class of the smart fluids, which will be exhibit variable yield stress. So these are generally are going to be discovered in by this in 1948 by Jacob Rabino and the US National Bureau of Standards. Then these fluids has the ability to change from a liquid to semi-solid or otherwise in the plastic state instantaneously upon the application of the magnetic field. So in semi-solid state, so this fluid exhibits the viscoplastic behavior. So generally they are we can able to characterize by field dependent stress. So and this field dependent yield stress and then it is going to be with respect to the very faster in response time. So these fluids, MR fluids, have the attractive technology for many applications, like some of them we can say that the dampers are and brakes, we can have clutches and hydraulic valves, seals, actuators, right, composite structures, and even prosthetic leg also generally are going to be people are developed, as well as they have used in washing machines also. So there are a lot of potential applications are there of this MR fluids. So if you take this, MR fluids are generally, generally we short in metallurgical fluids, we generally call as this in short ways MR fluids. So these MR fluids generally, in the absence of magnetic field, generally they are free flowing with a consistency similar to this almost motor oil, like light consistencies, like light viscosity is going to be there. So generally we can call it as a Newtonian behavior. It can be observed in this case of when this in the absence of magnetic field. So while the value of these fluids is realized when the magnetic field is applied, so this micron-sized ferrous particles suspended in this fluid align parallel to the flux path, creating a particle change. Initially, the ferrous particles are in amorphous state, means nothing but randomly they are going to be oriented in the oil, any carrier medium. And then once we apply this magnetic field, generally the particles, the ferrous particles, begin to move along the flux path. So these particle chains resist and restrict the fluid movement. So because of this, yield stress is going to be developed in the fluid. So the degree of change in the related to the magnetic field strength may occur in the. This is generally going to be happens in the form of in the milliseconds itself. So because of that, only a lot of potential applications are going to be there of this MR fluids. So before going for this, that what are the MR fluids are going to be? So in MR fluids, so micron-sized particles, when carbonyl iron particle generally we call it. So these are generally are going to be a soft magnetic particles. So these are dispersed in a carrier medium, which is generally either mineral oils, silicon oils, kerosene, and water. Depends upon the type of the application. So generally in dampers and other applications, the people will use this mineral oils and silicon oils and kerosenes. And whereas in polishing, generally people prefer to go for water as a carrying carrier, otherwise we can say liquid as used. So we can, this is some image of where taken just a minute. Same image of this when carbonyl iron particles. So when it in the liquid state, when without magnetic field, the field looks, the MR fluid will looks like this. Once the application of magnetic field depends upon the type, how the magnetic field orientation is going to be. Based on that, it will becomes as a stick or like kind of a duff. It becomes almost a. So what are the properties that are required for when we are using as a particle which is consists of 1 to 10 micron size of magnetically polarizable, soft magnetic material is going to be used in this metallurgical fluids. So for that, this channel is going to be permeability is a very important thing. So generally, this we once how can define the degree of magnetization of material that will be respond linearly to an applied magnetic field. Right. So when when you take any magnet or any iron pieces generally, so when without any magnetic field, generally when it is experienced into the magnetic field, so the bulk material domains usually all this ferromagnetic materials have this domains are going to be, so those domains usually cancel each other. They're leaving this material is unmagnetized, means nothing but all the domains are generally are going to be randomly oriented in the in material. Once they experiences the magnetic field, so based on this the field path, generally all these domains will parallelly orient into direction. So because of that, even some of them, these magnetic materials are generally are going to be, they'll change in their size also, means nothing but there may be contract and distraction also is going to be contraction and expansion also going to be takes place. Because of that, other applications are going to be there for this. Anyway, I'm not going for in detail about all those things. So once the same type of is going to be used, like instead of bulk material, here we are using as a smaller particles are generally are going to be used. So if you see, generally iron generally can have the relative permeability is going to be 2000, and nickel generally 100, and other peoples are going to be. So mostly here we use this thing. Another important property along with this permeability, another is going to be corrosivity. So this is nothing but where like when you are magnetize the any material. Let me one minute. When the material is generally is going to be magnetized, generally what happens means, generally if you see this BH curve, generally this will crosses the 0, right? And then once it is demagnetized, generally it will come back, come back the another path. So the difference in the path where you can have like a crosses 0, which is generally we call as a corrosivity. So if you have the more and more corrosivity is generally is going to be there, the material is going generally we call as a hard is going to be harder. When the corrosivity is generally the gap between this, where magnetization and demagnetization is generally is going to be less generally. So in that, this is generally can have the soft materials. So generally for Mrfa fluid applications, we'll prefer to go for where the magnetization curve, again, it has to follow the same thing, magnetization and demagnetization without leaving any kind of remittance in the magnetic field is not there in the completely on the any iron particle, then generally is going to be suggestible actually for the for use of this in the Mrfa fluids. And also another important thing is generally is going to be saturation limit. So when whatever you are applying the field, so in the in which all the magnetic field domains align in the magnetic field, only up to some saturation level only. Beyond that, if you are even if you apply them too much of magnetization also, generally they don't, the magnetic, they'll experience magnetic field strength is generally is going to be only what up to the limit only. So that is another thing. So it depends upon, like based on this, generally you can permolite generally can have the corrosivity 0.5 to 1. And even this metallurgical fluids, if you see, generally their saturation magnetic flux density almost generally is going to be 21,500 is going to be there. And pure iron in the form of, if you are going for the 99.95% pure iron form, if you are taken, so that maximum permeability we can get it on 10,000 going to be, and then saturation generally is going to be 21,500. So based on this, generally people prefer to go for carbon iron particles are generally are going to be used, which are generally are going to be purest form, almost 99.995 purest form they'll take it. And right, so particle size generally are going to be 1 to 10, and permeability should have the more and higher maximum permeability is going to be there. That will be better with taking into consideration of the corrosivity also into consideration. And then saturation depends upon the material to material, then saturation levels are generally are going to be there. And to disperse all these iron particles, so we need some kind of a carrier medium is going to be required. Those carrier medium should be non-magnetic in nature, right? And how much amount of generally is to be added, like what will be the percentage of particles generally is going to be added by either by weight or otherwise by volume. So this generally, I mean, based on this previous researchers and experiences, and then people have done a lot of experimentation. So it depends upon the type of application. It may go to like a 20% to 50%. In case of the polishing, we generally prefer to go for only 25% to maximum 30%. And because remaining abrasive particles also going to be there for a polishing purpose. So generally it will be limiting to 40 to 50% is 40%, and remaining that we have to go for almost 60% is generally is going to be a kind of a carrier medium. So if you increase the more number of magnetic particles, obviously we'll get the more magnetic effect generally can be able to observe in this case of so this fluids, like in the absence of magnetic field, then we already told you, like, so generally these are free flowing, will have the consistency is going to be almost near to this motor oil. Almost generally behavior is going to be Newtonian behavior. We can able to observe it. Once they are going to be, they'll experience as the magnetic field. So generally they'll change, I mean, according to that, I mean, they feel this magnetic field strength. So generally they'll change their yield stress behavior also generally is going to be develops. That will be changes according to that. In order to characterize these MR fluids, so generally most of the people will prefer to go for like a Bingham plastic model. So in this where the when the experience field stress is generally is going to be depends upon the independent yield stress as well as generally plastic viscosity, and then based on that shear stress. So the critical value of the shear stress is necessary to break the structure that is generally we call as a apparent yield stress of the material. So and then the strength of the magnetic field generally is going to be increases as well with respect to this applied magnetic field strength is going to be. That one more thing we need to be take it into consideration is going to be saturation as also have to take it into consideration while going for how much of magnetic field is generally can able to get it. So and so even some of the researchers, they reported yield stress of 100 kilopascals at a flux density of like 1 Tesla for 40% of the iron-based fluids they observed, and they got it. So measure in this cases generally can have the particle shape, size, and the density, particle size, how the distribution of these particles are generally are going to be, and what will the saturation magnetics is going to be, as well as the corrosive field. These are the generally are going to be important characteristics of in terms of this generally is going to be iron CAP powder or otherwise iron powder. And other things, when you go for based on this thing, when base fluid is also another important thing as going to be. So these people, because we use this in MR fluids, generally iron particles are generally are going to be 1 microns to 10 micron size generally is going to be used, right? So generally if you keep it aside for some time, generally what happens the settlement is going to be takes place because of the density. So they'll settle in the bottom side, and then redispersion is also another important thing we need to take care of while magnetic field is going to be applied, or otherwise if you wanted to think. So for that, generally in order to reduce the settlement and then redispersible, generally sometimes we also use some kind of a surfactants are generally are going to be used, as well as some, because iron is generally is going to be most vulnerable to the corrosion. So when you are using some kind of water other kind of medium, generally anti-corrosion additives also has to be added things. So these also base fluid like surfactants and anti-corrosion additives also an important factors that will be affect the rheological properties, stability, and redispersibility of the MR fluid. So there are so we the benefit of this controllable yield stress in MR fluids generally is has been realized, and most of the people realized, and then these are generally are going to be used in these whatever the devices which are made with the MR fluids are used in various applications also. So the range of applications are generally indicates the potential development or otherwise potential for the future developments also, right? In many of the applications when you see MR fluid is applied devices, so generally is going to be employed in three common modes are going to be. One is going to be shear mode, other is going to be a flow mode. The flow mode is also generally is going to be called as a wall mode, and other is generally can call as a squeeze mode. So this both the shear mode and then wall mode, or otherwise we can say that flow mode, both generally are going to be commonly used in the to make the MR dampers. And other applications of this generally going to be a shear mode is we can go for MR brakes and then clutches, as well as I mean, like checking and locking devices also can be like a kind of use can go for. In case of the flow mode, the fluid is generally is going to be flows between the parallel plates. In the just only can go for in the second one where we can in the flow mode. So where the fluid is generally is going to be forced through the in between the two fixed parallel plates are going to be. So now in shear mode, where you can say that the fluid is going to be flows in between the parallel plates, but they are going to be sliding relative to each other. The first one is generally is going to be where the magnetic MR fluid is generally is going to be stationary, and then the plates are moving relative to each other. Whereas in case of the flow mode, generally the plates are generally are going to be fixed, and then MR fluid is generally is going to be driven by. Another mode generally we can have, where in flow mode we can go for shear walls, servo walls, and then shock absorbers, and then dampers are generally are going to be used in this case. Another application where you can go for the squeeze mode, generally people will use less in that, less common, compared to the other two. Actually, these are generally are going to be used for small amplitude vibration, vibration mitigations. For that generally is going to be used, and for high force applications generally are going to be used. So finishing will come under this category of squeeze mode. So most of the finishing applications will come because, and then there will be shear stresses are generally are going to be developed while it is forcefully applied, and then how the movement is going to be applied to that. So like a lot of applications are there for we can be benefited because of the controllable yield stress of this MR fluid. So right, generally the first people are devised, the device which are generally are going to be made by this is generally is going to be MR dampers. So these are generally are going to be used in automotive industry as well as in the civil engineering community also. This where bridges applications they'll use it, as well as even seismic applications also they use this MR dampers. And they are going to be studied because of their ability to respond very quickly without providing while providing this large dynamic forces. Right, and like generally if you see go for like hydraulic dampers, MR dampers are generally are do not require any mechanical walls are not required, right? To restrict the flow. Instead, generally they use this electromagnetic coil is generally is going to be incorporated into the piston, and reservoir is generally is going to be filled with MR fluid. With the application of this current, with the wires, right, a magnetic field is generally is going to be developed in the annual orifice. In this annular orifice, this magnetic field generally causes the yield stress to develop in the fluid, and it is going to be passes through this MR fluid going to be passes through the magnetic flux path, so which will be increases the apparent viscosity generally is going to be increases of the fluid. So because of their ability to offer controllable damping force with a minimal power requirement, so these dampers are generally are going to be considered semi-active damping elements. So this is in the form like and they have these dampers are served as solutions to many engineering challenges also. This is one of the typical damper assembly, complete assembly done by this large corporation. Another is generally where you can have applications of an automotive industry. So in automotive industry, particularly, we can take this, have taken particularly the advantages of MR fluid dampers. So real time, and then as a semi-active damping elements. So first, it is going to be produced by, Crossby and Cornop. And then they like semi-active suspensions have been shown to offer this valuable benefits of the vehicle primer suspensions. In 2002, I think so, Cadillac, they developed this MR active suspension system in its premium vehicles actually. Even afterwards, generally that Audi and even other vehicles also, they started using this as a suspension system. So generally now they're having a different type of suspension, like magnetic ride control suspension systems are going to be there in almost like even Chevrolet also generally offering this kind of. So if you see this, I mean, like it is going to be demonstrating the figure. It's going to be demonstrating, which is the yellow one is generally has without any magnetic MR fluid suspension system, where it can have the other vehicle is generally can have MR fluid. So this 60 kilometers, I think so, 60 miles per hour over right, and then handling loop at the generally where you can have the superior control of MR suspension is going to be there in case of I mean. So with this generally where you can have this vehicle like I mean, vehicles secondary suspension systems also generally are going to be good candidates for this MR dampers. So even large corporation also developed in some or other application, I mean, MR damper, I mean, different type of MR damper for semi-active seat suspension systems. This generally semi-active seat suspension system for large and on-road and off-road vehicles they used. Particularly that generally they call as this motion master, right? Which is developed by this large corporation, which will be consisting of like a damper and when have the control unit also in this. So this generally, I mean, like this is generally is going to be like a kind of retrofit to this existing hydraulic truck seat dampers, actually. And this generally, also, I mean, like even they gone for this, I mean, applied this, I mean, in case of agriculture off-way vehicles also, I mean, they use this motion master system, and even for I mean, when school transportation officials also, I mean, they have they are using this I mean motion master systems are generally are going to be go for like nothing agriculture, and then off highway equipment also they are using this thing. So whereas in go for like not only this, and then we can also have the structural applications also, structural control of applications also. So generally again, so these are gained in, I mean, attention in structural control applications. So seismic response reduction using this MR dampers, one of this research area which is, I mean, received considerable attention recently. So large scale MR dampers have been considered for structural vibration mitigations. So here, I mean, this is one of the damper where the full scale MR damper has been designed and then built in order to test the stability of engineering applications, I mean, sorry, civil engineering applications. So these are like they have even they used for this cable stayed bridges also. So first one generally Dongting bridge generally is a cable stayed bridge which generally crosses the Dongting, I mean, lake in China. I mean where and so in that in the, I mean, like they in this Dongting bridge became the first cable stayed, I mean, bridge which will use this MR dampers to suppress the wind and rain induced vibrations. So which will be resulting in the indicate significant in the vibration control effectiveness in the cables and that were damped with the MR dampers. Even other people also try to go for the structures, I mean, like where they are going to be prone to earthquakes, other things. They're I mean, building, I mean, civil engineers or architects, they are starting to use this dampers in case of so one of the architecture is I mean, civil engineering architecture developed the structure is going to be with the MR damper by using MR dampers. So this generally has used, I mean, these MR dampers also considered for use in structural tuned vibration absorbers also. Damper generally these need to be provide like a sufficient damping force while still maintaining a low off state force. So another thing is MR sponge dampers generally are I mean when is one of this people are developed these are generally are going to be MR sponge damper coupled with a tuned vibration absorber can provide this benefits of controlling unwanted vibrations in the structure. So inherently this inherent difficulty with this when tuned vibration absorber in the structures and is generally is the inevitable off tuning of TVA due to changes in the system's operating conditions. Mass or even stiffness changes is going to be takes place over the time. Right? And then this off tuning can lead to the degradation of its performance of the tuned vibration absorber. So people are developed with TVA along with the MR damper. They added this MR damper to the TVA so that the sensitivity of the TVA is going to be changes when the even the system operating conditions are generally are going to be when reduced also. So because of low of state damping, MR sponge diameter generally is going to be a good candidate for this kind of applications. Like this MR damper, like a sponge damper, generally is going to be MR fluid is generally is going to be absorbent matrix. In case of like a sponge, often open celled foam, or otherwise we can go for fabric also. This sponge keeps the MR fluid located in the active region of the device, where magnetic field is generally is going to be applied. So the device is generally is going to be operated in the directly shear mode with a minimum volume of MR fluid. So moreover, generally when you go for dampers and other things, so generally we require to have light of sealing is much more is going to be required, right? So even rod surface finish is also another important thing need to take care of. Even precision mechanical tolerances also need to be taken, because the gap between this inner rod and then outer aluminum generally is going to be very minimum, the gap between that. So because of that, generally we need to be maintain good surface finish, as well as the tolerances also. Geometrical tolerances also need to be maintained very tightly. But when you go for this, like a sponge dampers, we don't need to be worried about all these things, because this in the fabric, like in the sponge, these are generally MR fluid is going to be containing. And also it is going to be cost sensitive also. Where can have the like cost sensitive applications mean nothing but we cannot able to afford that. What are the dampers which are generally are going to be developed by this a lot of people or other people, where they are going to be applicable only for premium automobile industries only. So those things generally cannot be able to apply in case of the domestic application, like a kind of washing machines, other things. So this will be generally we can able to use in case of this domestic washing machines. So where MR sponge diameter is generally is going to be used in case of even metal washing machines also. But otherwise generally is going to be another is generally where innovative generally can able to use for this is this MR damper, Lord motion motion master damper, which generally is going to be used in even a prosthetic leg also, which is generally is going to be developed by this in German people. That this generally where this whatever the device which is generally is done with like a motion master damper, which is used in the prosthetic leg, so dramatically improves the mobility of a leg by mimicking a natural gait. So, and these are coupled with a combination of sensors and controllers. So this, the device can adapt by varying the movement ranging from, you can move up, uphill and downhill motions also, and the straights and even bicycling also can be able to do with using this damper by using in the prosthetic leg. Other common, commercial application is we can use this. I already told you about this large suspension, seat suspension system, which is already used, and with along with the controllers, we will have it. Other, commercial use of MR fluid is generally is going to be a rotary disc. So, a large corporation generally currently manufacturing this MR rotary brake, which can be used for exercise equipment, and then a pneumatic actuator, and steer by wire systems and other similar applications also they are using this MR dampers. So these devices have controllability and fast response time, generally within 10 to 30 milliseconds itself, generally, or otherwise sometimes even 10 milliseconds generally can have the response generally becomes as a solid to, liquid to the solid, so that generally can even response also generally is going to be more. So because of that, people will prefer to go for the braking also. High power, high torque at lower speed we can able to get it, and requires very less power is going to be required to apply this brakes. So and along with this, generally we can have this device include the ease of integration, or like easily we can able to integrate with, and then program, even programmable functionally, and then rugged in construction, and they are giving even long service life also. So, and nowadays I think so even RD cars, and then BMW, these cars also they are applying this MR fluid based brakes generally are going to be applying. Previously they used to go for heavy vehicles, heavy trucks, other things. Nowadays they are going to be prefer premium vehicles. They are using this MR fluid based brakes also. Other than that, we can also have the semi models. Clutch is also generally is one example. Another is going to be, you can have this engine mounts where you can use for and just I'm coming back. Coming to this other application, innovative application in commercial applications is MR fluid is polishing the optical lenses. So this is QED technologies are generally are now currently they are producing this multiple axis CNC polishing machines. We use a slurry made of MR fluid, completely exactly MR fluid. Whatever we take for the damping other applications, we don't take it, and then need to be add some kind of abrasive particles are generally are going to be added into this. So here, the fluid MR fluid which is used for this applications are generally are going to be called as a MR polishing fluid. So this slurry made of fluid and then abrasives are generally are going to be. So when the fluid is generally is going to be delivered to the wheel, right? So it looks like almost this is the latest one actually developed. After this they developed a very latest one. It looks like almost all kind of a grinding wheel only. Bottom surface you can go for, even very flat surfaces also, like heavy high diameter jobs also can be able to go for, even small jobs also can be able to go for using this thing. So first in this I'm just going for my actually my specialization in the machining area. So I have done my PhD in MR finishing. So I'm just slowly moving to this MR fluid applications in finishing actually. So whatever I taught, just only these are the brief introduction about MR fluid and then MR fluid application in other than this finishing. So like in 1988, like scientists at Belarus generally explored the possibility of using this slurry comprised of aqueous, aqueous means water-based metallurgical fluid where they used cerium oxide as abrasive to polish the glass up to nanometer level. For that they have used like kind of like and after that they gone for the 1990 generally Korondowski and others Jacob, other people they developed further in the Center for Optics Manufacturing at the University of Rochester, and afterwards it is that process is generally they use they called as like name it as a metallurgical finishing, and to determinately polish the optical flats, spheres and aspheres also. And after that generally again they typed up with this QED technology. They produce now all MRF machines are generally are going to be produced in the name of QED technologies. So in starting generally where if you see this in 1996 they developed even time in a typical MRF system, which will be can have the completely with the functions like fluid circulation, mixing, and then heating, dispersion, other things is there can. And now we have even already told you there are multiple axis CNC polishing machines are developed, and mainly they use for only to polish the glass materials only. So in this case, the first when you're going for like and then here we can have the North Pole, and we can magnetic is magnetic permanent magnets generally they use to so the permanent magnets and then in this dow generally they magnetic field is generally is going to be kept it. So when the it will experiences the magnetic field, and then other side we can have this lenses are generally are going to be, the lens has the rotational movement as well as we can have the rotational movement is going to be there, as well as we can have the when it can rotate angle with or otherwise we have the linear movement with respect to the vertically. So any shape can be able to produce it using this metallurgical polishing. This is the first they done instantly. Afterwards they developed this kind of MR fluid. So what is the major challenges generally when you go for this traditionally we do polishing with of these glasses. So generally traditional methods we use this finishing of like Princeton lenses and ceramics, mostly generally you can say that brittle materials like lenses, ceramics, and then semiconductor wafers generally are for polishing all those things are generally is very expensive and as well as labor intensive also. So mostly all these materials are generally are going to be made up of all these precision lenses. Mainly is going to be brittle materials only, right? So what happens means while they are going to be machining, generally they'll try to, they'll tends to fail by cracks actually. So even single crack is there, so drastically they'll affect the performance of the lens performance, right? So that it will be, so that lens is completely ineffective for intended application. In case, for example, if you are going for the IR camera, infrared cameras are going to be there. There will use the lenses. So any small crack, small crack, or otherwise a small pit, whatever it may be. So that will be, visibility is generally is going to be so drastically is going to be affected. So compulsory every device which is generally is going to be used for for example, like lasers or otherwise fiber optics, so requires very high precision lenses are generally are going to be required. So it will be every year, increasing in its demand more than ever. Right? So this lens manufacturing in traditionally they'll do in two steps. One is generally is going to, they'll do first the grinding operation, and then they'll go for the finishing applications they'll do. And while doing this grinding, generally they'll lens to get the closer desired shape and size, while this fine finishing generally is going to be removes cracks, and then any tiny surface imperfections are going to be there. Those also generally are going to be sometimes generally are going to be either removed, or sometimes generally are going to be overlooked, or sometimes they are going to be even small pits also generally are made form because of the while doing the polishing operation. Small abrasive particles may embed it, or otherwise may lead to the small crack development also. So because of this generally, so they'll go for in-house opticians. They use, these are generally they'll employ for finishing a purpose. So generally they have to done with the hand only, so manual grinding and then manual finishing only. So because of that, generally it makes this a very labor intensive process, and then it is generally odorous also. So what is the biggest disadvantages to when you go for manually grinding and then manually finish it? So generally we cannot able to get the exactly the accurate, as well as so we cannot able to ensure that entire surface is generally is going to be polished without having any small damages or any imperfections, right? So to overcome all these difficulties, generally this Center for Optics Manufacturing in Rochester, already told you, so they developed lens technology, so that they can go for automatic lens process, which we generally call as a now metrological polishing, or otherwise you can say finishing process. So in early days they used to go for even 10 to 100 nanometer peak to valley height, as well as generally you can say 0.8 nanometer surface finish they achieved in optical lenses. So already this in this case, when you see this the figure like MR finishing tech means, so we can able to finish a convex flat surfaces or otherwise concave work pieces also. Generally is going to be positioned above this reference surface, right? And the lens is where you can have here we can able to keep this concave or whatever the lens is going to be, we can able to keep it. And then MR fluid is generally is going to be deposited on the rotating wheel. So here we can have the electromagnet is going to be there. So so by applying this magnetic field in the gap, the gap, so the MR fluid becomes stiffened, so that the stiffened region forms as a kind of a transient work zone, or otherwise you can say called as a polishing spot. So surface smoothing and then the removal of subsurface damages and figure correction also can be able to accomplish by using this rotating the lens on a spindle at a constant speed, and as well as we can also sweep the lenses about its radius of curvature through the stiffened finishing zone. So material removal is going to be takes place due to the shear stress, which is generally is going to be created as the as metrological polishing fluid is going to be that ribbon is dragged into the converging gap between the part, means nothing but the lens and the carrier surface, which is generally called as a moving wall. So the zone of contact is generally is going to be restricted to kind of a spot only, which conforms the perfectly to the local topography of the part of the whatever the lens we are. Either depends upon the concave, convex, or flat. Depends upon that. Generally, the zone of contact is going to be restricted to a kind of a spot. So deterministic finishing of flats, spheres, and aspheres can be able to accomplished by mounting this the lens on a rotating spindle and sweeping it through the spot under the using this computer control. Completely, all these things are generally going to be computer control. So but we are allowing some time in the thing we can go for dwell time is generally is going to be determine the amount of material removal also. So what are the merits of MR polishing, metallurgical finishing over the traditional lapping process, we can say. So it is accomplishes the, the MR fluid ribbon generally can be able to adjustable through the magnetic field, right? So how much of force, other things also generally can go for, and it also carries the heat and debris away from the polishing zone. Another is going to be it's not like a load like kind of like a grinding wheel. So grinding wheel, the chip loading is going to be takes place, but here it won't be there. As well as it won't lose its shape as it is. It is going to be deform. It's self deformable. So generally it does not lose the its shape. So that generally the wear won't be takes place, nothing but you can say. So computer control MRF process, ability to produce, get the surface finish accuracy, as I already told you, 10 to 100 nanometers by valley, like to overcome many fundamental limitations which is generally going to be there by inherent to this traditional finishing techniques. These are generally going to be efficient. MR fluid, which is under the MRF finishing is going to be an efficient and able process for precision finishing of optics. And then this makes the free form shapes possible for the first time. So then lot of so even they finished by using this endoscopes, and then where the collision avoidance devices, which are generally is going to be used for the industry and scientific testing devices, and right. So military night vision equipment infrared binoculars, all these things generally they use this lenses are generally are going to be very most lenses are going to be all these lenses which are used in these things are generally are going to be polished by this using MRF process. So, and even people, depends upon the type of abrasives. Even sometimes even nano diamond doped MR fluids removes this edge chips, cracks, and then scratches in the synthetic sapphire bend bars also are generally they achieved. So this is the one actually shown. And so what is MR polishing fluid? As I already told you, like MR fluid is generally is going to be micron sized magnetic particles are generally are going to be dispersed in a carrier medium and in a non-magnetic and then we are adding in MR polishing fluid non-magnetic abrasive particle, non-magnetic particles which are generally called as abrasive particles are generally going to be added. And then along with that, because of already told you, so there will be a problems are going to be sedimentation is going to be one problem, and then redispersion is another problem is going to be there. So in order to reduce those things as well as generally corrosion problems, so we use even some kind of additives are generally are going to be added. So even sometimes people will call as even surfactants also are going to be added to this MR polishing fluid. So MR fluid is without addition of abrasive particles, generally we call as MR fluid. So once if you add the abrasive particles, generally people will call MR finishing fluid or otherwise MR polishing fluid. People have the different names, generally they'll use it. So another variety by these are QED technologies that developed, which is generally is going to be MR jet polishing is going to be. So when you go for water jet machining process, all these things in order to polish the materials like a glass, any brittle materials we can say, or diamonds and ceramics, stainless steels, even sometimes hard, stainless steels also generally they'll try to finish with this water jet machining. So the surface quality mainly depends upon when you're going for this water jet technology. So the surface quality generally strongly depends upon the one is going to be the size and the impact of angle of the abrasive particle. right? So you need to be do some appropriate adjustment has to be done, like jet velocity we have to be control, abrasive sizes, and then concentration of depends upon this, so that we can able to control the surface finish on the workpiece material. And one more thing is generally this whatever the abrasive jet, water jet we are using, right? It loses it coherence as once it will exit from the nozzle, right? So because of combination of abruptly imposed longitudinal and lateral pressure gradients are going to be there, as well as we can have the surface tension forces are going to be, and there are aerodynamic disturbances also going to be there. So the destabilizing aerodynamic disturbances can be able to increase by with the one is going to be, we can increase the jet velocity, so we can go for, or sometimes you can also add some kind of stabilizers also. Long polymer chains, other things are generally are going to be added to get the more stabilization along with the jet velocity. So for this region, generally it will make the diameter of the nozzle water jet generally is going to be for cutting applications. We use very small, so that we can have the provide this high precision, high pressure machining, as well as the high unit pressure also we can able to get it. And also we keep it like the nozzle should be very close to the workpiece surface. Generally the standoff distance is generally is going to be a smaller one actually. So in these cases also the standoff distance is always will keep it as the twice the diameter of the, almost near to the twice the diameter of the nozzle. But for high pressuring, a stable and relatively high speed and low viscosity fluid jet, which generally remains collimated, right, and coherent before it impinges on the surface, is generally is going to be required for any neatly if wanted to polish the, or otherwise you go for high pressure finishing is going to be required. So because of that, they tried with the stabilized jet of meteorological fluid, containing this again, abrasive particles are going to be is magnetized by an axial magnetic field. Like when it is flows out of the nozzle, means like where are they going to be, standoff distance is going to be, so it is generally is going to be local magnetic field is generally is going to be there, so which will be induces this longitudinal fibrillation, means nothing but stabilizing, as generally is going to be, it acts as a kind of a stabilizer, and high apparent viscosity within this MR fluid is going to be there. So because of this, generally this magnetic field adjacent to the nozzle, which will be result in the suppression of all the initial disturbances, or what are it will take those disturbances, which will be overcomes that. So because of that, which MR fluid which is ejected from the nozzle, highly collimated, and then coherent jet we can able to go for, right? So but once this jet beyond, it will pass beyond the magnetic field, it generally it again gradually begins to decay, means nothing but again flaring, other things is going to be takes place as a, it leaves the coherent, it won't, you can't get any coherent, but until unless it is in the exposure of magnetic field, generally we can able to get the highly collimated and coherent jet we can able to get. So in case of the, we can go for back to the water jet polishing, abrasive water jet or otherwise water jet finishing, we go for. In that cases, the jet, water jet will remain stable. Maximum is going to be up to 2 times this nozzle diameters. So that's why generally we keep the almost standoff distance is generally is going to be very important, and it plays very crucial role in case of even abrasive jet machining or otherwise water jet machining process. Right, but especially if we go for the water jet, generally it will loses the coherences beyond certain limit. Generally it is going to be 2 times the nozzle diameter is going to be there. So, but in case of MR jet when polishing, so the coherent portion is generally can able to extend it because of this magnetic field. So 7 to 8 times the diameter, means longer standoff distances we can able to go for. So because of that, this will be very attractive for finishing of complex shapes like freeform optics, steep concaves and cavities can be able to easily we can able to finish it. So this query technologies which is done, they got it even 10 nanometer surface roughness on and we can go for even 1 nanometer RMS on complex shapes like freeform cavities and steep cave, steep concave optics. Generally they got even they are done experimentally and they proved also actually. Nowadays they are going for if you see this is generally where the with just only water, then we can have here starting with from flaring is going to be takes place. Even if there is no MR, like no magnetic field, even this MR fluid also losing this coherence initially itself, almost near to this. And when the MR fluid is magnetic field is going to be on, in that cases, the stabilization is going to be more like a coherent in nature, and where we can go, nothing once this, if there is no magnetic field means nothing but again the MR fluid also loses its magnetic field. It loses the coherence. So even they got like a peak well-reduced parts generally when they have done machining using this jet polishing, like a 1.5 diameter, 1.5 mm diameter jet upon the stationary flat fusical, fused silica they used to finish the fused silica. And the distance between the nozzle exit and then part surface, generally they keep it as, standard distance between the nozzle and the part is generally going to be 50 mm they use for both applications. Right, and then based on this volumetric, so generally, based on the distances, other things like the dwelling time is nothing but the finishing time. So generally, amount of material removal is also going to be based on that only. So based on this, generally we can able to polish it. Even steep concave shapes and convex shapes also can be able to go for. So this is a photograph I have taken from one of the literature paper, where outside generally can have the aluminum shell, inside generally can have the glass insert is going to be there. So for those things, generally they have finished with this MR jet, ogave shaped kind of things they have they done. Another important process is generally is going to be Mrfa process, where so this process is generally is going to be a combination of two things. One is generally we can have abrasive flow machining process, which is generally is going to be used to finish the inside the kind of cylindrical holes wanted to finish it. In those cases, generally abrasive flow machining is generally is going to be widely used. So this process is generally is going to be used for both. It is a combination of what I can say that both the MRF process and then combination of AFM process also, abrasive flow machining also used. So combinedly, they're done in the metallurgical flow, abrasive flow finishing process, which is done in IIT Kanpur by my guide. So, and then afterwards, there are a lot of variations also came into this in this case. So in where I can say like traditional metallurgical finishing is going to be the smart is going to be, and then it is going to be forced through one side to the other side actually. So because of that, where you can able to finish the different type of inside surfaces can be able to go for like even in part of concave and convex shapes also can be able to we can, finish it with a nano level surface finish. So it is like a hybrid process, we can say. So here in this process, like a magnetically stiffened slug of like MR polishing fluid where is extruded from one side to the other side. Like we can say go for like a back and forth through the finishing area, which is generally is going to be the finishing area is generally is going to be formed by this workpieces and then fixtures. So the material removal is generally is going to be occurring only where occurs as the specified areas where magnetic field is generally is going to be applied. It's not completely throughout, it's not annually, it's not going to be applied, only one side is going to be applied. So only the area which is generally gets this magnetic field. So in those areas only generally the finishing area generally is going to be formed like a work. Finishing area is going to be removed. So material removal only where the magnetic field is going to be, right? It will, there generally, remaining areas generally are going to be unaffected. Only the areas which is generally is going to be receiving the magnetic field, those areas only is, material removal is going to be takes place. Mostly, one is generally can have the normal force is going to be applied, because once it is going to be extruded through and back, like have extruded through and back, generally what happens means generally the shear stresses also generally are going to be developed. So because of that, material removal is going to be takes place. Another important thing is in this cases generally are so even the people, the researchers has tried to see that how this magnetic field is generally, when the magnetic field is applied, so how these chains are generally are going to be formed by embedding the abrasive.
Madam, we cannot hear the voice, madam. Hello, madam, can you hear me? Hello, participants, can you hear the voice?
Yes, ma'am.
Yes, ma'am. It's okay. What is there?
Can you hear Saraswati madam voice?
No. Now it is almost not accessible.
I think madam will join again.
I think otherwise some signal problems, network problem.
Disconnected. Already messed out. Due to network problem. Hello, madam. Call to personally. Madam.
Just wait, madam is connecting again. Srividya, are you with madam? Madam. Okay.
Sorry,
Okay, madam. You can continue.
power is gone. I'll continue. I'll share the PPT. Madam, is it okay now?
Okay, madam. We can see.
Okay. I'm sorry once again. So this, I mean, like when a magnetic field is going to be applied, so iron particles embed in this, I mean, abrasive particles are generally are going to be embedded in between the magnetic chains, and then we can able to even show it. I mean, they, I mean, done the experimentation in the same, I mean, like so the same photograph is indicating that abrasive particles are generally are going to be embedded in this abrasive particles, I mean, chains, and when a magnetic field is generally is going to be when they are experiencing the magnetic field. So in this case, is the magnetic field density and is very important parameter, most important parameter to improve the surface finish, along with the number of finishing cycles, means through and fro we have to be forced through this medium, right? And then another thing is going to be how much of extrusion pressure we are applying to. So and even they succeeded up to, I think, 30 nanometers I mean, on stainless steel workpieces. So they achieved the surface finish also. When completely they gone for the, after grinding immediately they gone for this finishing of applications. So generally even they'll try with this different type of abrasive particles also, like silicon nitride, and then I mean, those things. So but generally hard materials, generally surface finish improvement is generally in case of hard materials is generally is going to be less compared to the stainless steel workpieces. So and another and like but like when we can able to clearly we can able to see that. So as the magnetic field density increases with when the application of like magnetic field density is going to be increases with the increase in the current, right? So when the magnetic field density is going to be increases means nothing but there will be a change in the surface finish. I mean roughness means surface roughness is decreasing, as the first one is going to be the first graph, I mean like a line is going to be is indicating that I mean there is a change in the surface roughness. How much will be the change before and after? So we can able to improve that. It is made 0 to 0.13 microns changes is happened when they gone for. And this is the like before, I mean just only after grinding. So at 200 magnification with the simply done with I mean without any magnetic field, but they have I mean like a force through 200 cycles, but that surface generally can see that means the same images, so which will be indicating that there won't be any kind of a finishing is happened in the first one, the first figure. But when after means once you apply this magnetic field like 0.5 time Tesla and then polished for 200 cycles, and then we can able to see that generally there is will be only the grinding scratches are generally are going to be visible in this both the cases. Only grinding scratches initially which is developed by the grinding process that are generally are going to be visible in this cases, which will be indicating that generally where you can say that without magnetic field means nothing but the fluid flow only randomly it will flow, and then I mean these abrasive particles don't have this bonding strength. So because of that generally they'll just only moves over the I mean it will roll over the surface on the peaks of the surface roughness. When peaks and valleys means the peak on the peaks generally it will roll over. While going for when magnetic field is going to be applied, so these abrasive particles are embedded. So because of that generally they'll get a bonding strength is going to be gained. So because of this bonding strength, so these are generally when they are moving over the surface, generally they'll try to I mean like when a shear force is generally is going to be applied, so generally it will scratch the material, and then material removal is going to be takes place in the form of micro to nano chips are generally are going to be I mean almost nano chips only we can able to get it well go for. So the bonding strength between this I mean the bonding strength obtained by these abrasive particles depends upon the how much of the I mean the force between the two particles abrasive chains are going to be. Based on that is going to be, if a current is increasing, so magnetizing current is increasing means nothing but even magnetic field strength of this is also generally is going to be increases. The strength gained by the even abrasive means CP particles also generally are going to be more. So because of that what happens means generally they'll get the I'm sorry. So another variety they develop is generally is in the same Mrfa process only, which is generally rotational. Instead of just only they use this stationary magnets they have used. Instead of that, they use this rotational Mrfa processes they develop. Means nothing but instead of like permanent magnets are generally are going to be moved surrounding to the workpiece fixture. I mean, rotational movement is generally is going to be applied. So due to this, the helical motion, better performance is generally is going to be achieved compared to this which is fixed electromagnet. Even afterwards, even they develop this rotating magnetic electromagnet also they develop. So generally, where this RMF means rotational metallurgical abrasive flow finishing process is capable of producing a mirror-like surface finish in the range of nanometer surface. Generally, can able to achieve it. I'm just not going for the much more detail about all these things because the time is approaching. So another process is generally is going to be metallurgical abrasive honing is generally developed by IIT Chennai people. So in this case, generally they use the part is generally is going to be immersed in a MR fluid, which will be contain MR polishing fluid. So abrasives are generally are going to be. So in this case, generally, when your magnetic field is generally is going to be applied for MR fluid, which is containing this MR polishing fluid and abrasive particles. So generally, abrasive particles are non-magnetic in nature, generally, right? So because of that, they'll move to the higher magnetic field to the lower magnetic field. So because of that, so towards the abrasive particles, generally towards this workpiece, generally have the lower magnetic field compared to the outer side. So because of that, so generally, and again, honing means nothing but we do like a rotational as well as we can have the reciprocation motion is going to be applied for the workpiece surfaces, workpiece which are generally are going to be held on the spindle. So they successfully they employed and then they got even good surface finish they achieved in this MRAH process, metallurgical honing process. And another varieties people are developed, a lot of different type of varieties people are developed. This is one variety where so in all these cases they use this permanent magnets. In case of like generally you can have the just only tabletop mounted one people are developed. So where you can have the tool is generally is going to be made up of with the permanent magnets and then and we have the X and Y movements are going to be there, and then Z movement is generally is going to be moved downward, upward, downwards. So when the permanent magnets, when the MR fluid is going to be applied, so that generally it will form like a kind of a ribbon. So it depends upon the how this magnetic permanent magnets are going to be placed. Here in this case, left side and right side they placed. So and then orientation of MR fluid is generally we can able to visible one side to other side. Even some other applications are done like kind of this application this way also. This is the one where the magnet is going to be. So and based on that, you can lateral surfaces also they try to finish with that. And more because the security technology is having this like a grinding kind of MRF process is generally they have the patents. So most of them are using in stuff that permanent magnets they are using. Another process which is developed in IIT Kanpur, where I'm when I'm doing my PhD, my colleague has done this ball and metallurgical finishing process is developed. So this is used for like previously once you see all these things generally concave convex shapes and other things only we can 3D surfaces of like a kind of dies, molds, other things generally we cannot able to go for. So this is developed to because to cater those kind of applications. So and this almost flat and 3D surfaces of either magnetic and non-magnetic materials also you can be able to finish it using this ball metallurgical finishing process. So in this process generally hemispherical ball is generally going to be formed using MR polishing fluid at the tool tip actually. Tooltip you can able to observe, right? So due to this magnetic field variation, the ball generally can able to have the variations. We can stiffening to light stiffening, and then you can able to control that ball stiffening also. So computer control 3-axis motion controller is generally is going to be provide the movement to the ball. So the stiffened hemispherical ball can be visualized like similar to this kind of a ball milling cutter is going to be, right? So and the 3-axis machines, I mean, like when you go for using this milling, those it like looks like the same thing. So that's because of that their name it also ball and metallurgical finishing process. So this process have the potential applications in, I mean, like we can go for like already been told you, like aerospace and automotive, molds manufacturing, semiconductor, and optical optics machining also can be done. So in this case, generally the tool geometry and then I mean in process control of tool geometry as well to control the finishing forces are going to be happen. I mean, we can take care. And I mean, already told you, so that the debris and then and the heat can be carried away from the polishing zone can be, and even you can able to finish it. Ferromagnetic materials or non-ferromagnetic materials also can be able to finish it with a nano level surface finish up to nano level surface. Even another thing is generally continuously, because the pressure polishing fluid is generally is going to be forced through. So I mean, we can continuously replenish the, I mean, the fresh fluid can be we can get it to at the tool tip. So there won't be and there won't be any kind of wear is going to be. So how it is going to be, right? So MR polishing pressure, MR polishing fluid is generally is going to be forced through, like the pressure is to enter this, axially from the upper end of the tool, like from here through the rotary wall, right? And once the MR polishing fluid reaches through this, like kind of cylinder kind of things is going to be there. So that through it reaches to this tip of the tool, I mean bottom surface where near to this workpiece surface is going to be. So these iron particles in the MR fluid generally is going to be, and when you apply this magnetic field, so this polishing fluid are aligned in the direction of magnetic lines of forces and form like a kind of a change, like a kind of a structure. And here the workpiece is also almost a kind of it may not be completely pure ferromagnetic material, but low permeability magnetic material is going to be there. It's generally the chains are generally going to be in perpendicular to that surface. Actually, it will take. So which will be once that when it is the MR fluid which at the tip is going to be experiences this magnetic field, so immediately it will form like a kind of ball kind of form is generally going to be formed. So this leads the formation of spots. Generally, we can able to the stiffened ball can be used for polishing the any workpiece surfaces. Already told you, it looks like almost a ball and metallurgical finishing, ball and milling tool. So because of that, they gone for. So this in this case, generally they use this MR polishing tool is generally is going to be placed on a vertical movement. They provided vertical movement, and then workpiece is have the movement of X and Y. So all these things they controlled it through the stepper motors. And this MR polishing tool, which is going to be have the concentric iron core is going to be, and then electromagnetic coil, and then we can have the outer core is going to be there. So rotational motion generally we can control it through servo motors. And then already told you, so workpiece is generally is going to be mounted on the rectangular platform, which will be have the X and Y movements are going to be there with this. So completely computer integration motor controllers are generally are going to be very precisely, they'll control this all these X, Y, Z motions. So based on that, generally we can able to finish the up to nano level surface finish. As part of my PhD, even I have developed myself this in order to, so we are talking about more polishing fluid, more polishing fluid. So to that, what are the factors, or otherwise what are the parameters that generally will be useful to finish the, or otherwise to polish the any kind of material? Depends upon the type of the material. We need to be know what are the, how the rheology is going to be placed, rheology is going to be placing. So for that we developed in the parallel plate magnetometer is going to be developed in the case because of the time. So I'm not going for much more details about this, and completely we developed in-house only. And then we done with the calibration of with the Newtonian fluid also. And then we also checked with this commercial rheometer with the commercial rheometers also. So after checking means like our rheometer is generally is going to be used for only viscous, when magnetic field is going to be applied, generally the field is generally, the apparent viscosity is generally is going to be increases, right? So for that applications, on state applications only we develop for that. Off state we cannot use our rheometer. So we done from preliminary experimentation, so that we experience like when the shear rate is increasing, where the shear stress is generally is going to be increases, but only for certain speeds only. Beyond that speeds, generally again because of centrifugal action, generally again the shear stress is generally is going to be coming down. Actually, yield stress, or you can say that whatever the shear stress is generally is going to be, it is coming downwards actually. Only for up to where you can say that the shear rates are up to 400 to 500, we are able to get the when the shear rate is increasing, shear stresses are developing. And with respect to the if you are applying the current, means nothing but magnetization is going to be there. So generally you can be experiencing the more shear stresses, generally we can able to experiences with this preliminary experimentation. And then we also gone for, because when you're going for the commercial rheometers are developed for only for MR fluids only. So in this MR fluids, generally they don't contain any abrasive particles, right? But generally when you're we already know that when you're applying the polishing fluid, means nothing abrasive particles are going to be there. And how these are generally are going to be affecting the plates of the rheometer. And that we just check it out. So we made it first to top plate and parallel plates, right? So parallel plates are generally are going to be, so top plate and bottom plate we made it to rough, and then afterwards we made it one is going to be rough, another is going to be like that. And when we have the both like rough surfaces are going to be there, then generally the shear stresses are generally are going to be more, because so rough surface is going to be peaks and valleys are going to be there. When the chains are generally are going to be forming, so the breakage, other things is going to be less in case of the, when you go for both the sides are generally are going to be made up of rough plates. Both the rough surfaces are going to be, like they are going to be in that. And then we also dry with like a different type of sizes of CAPs, like as well as abrasive particles are also very important thing, right? So we use two types of abrasives, and three types of CAP particles are going to be used. For this, how you chosen this, one is going to be like HS grade, OS grade, and CS grade. This HS grade is generally is going to be harder, mechanically harder one, and having the diameter is going to be up, like average diameter is going to be 1.8 to 2.3, and we can see this right. And OS grade is generally is going to be hard material, but it is mechanically hard, as well as it is also coated with the silicon dioxide. And that's abrasive size, like average size is generally is going to be 3.4 to 4.4 microns. Another is going to be used as a CS grade, which is generally is going to be mechanically soft, and then it is having that average size is going to be 6 to 7 microns. So most of the like IIT Kanpur and then IIT Delhi, so they use this, most of them is going to be used as a CS grade is generally is widely used actually. But we wanted to check it how these grades are generally are the sizes of abrasive particles are, sorry, sizes of the CAP particles are playing a role, as well as with respect to the abrasive particles. Right. So for that, in order to do the seriological characterization, means nothing but in order to check the shear stress and then viscosity. These are the two factors of rheological characterization we done. So for that, we use the three different type of models were used. So like a Bingham plastic model, and then Hershey model, and the Kazan fluid model is used. Right, as well as sometimes if people will use even along with that, power law also generally you can use it to characterize the fluid. So and then what are the data we got it? The data can we again try to best fit best fit it, right? And from this, what we conclude that. So we use this Kazan fluid model is generally is giving the better way. So that model is used to to in order to check the what will be the with respect to the what happens the yield stress with respect to the magnetization current. So as magnetization current is increases, means nothing but we are inducing the more magnetic field. So generally the yield stress is increasing for all the three fluids, right? And then yield right. So as well as for these are two, abrasive particles also we used. One is going to be rhodite, and then other is going to be, the sizes are generally are going to be different. And here the size is, rhodite size is generally is going to be more, and then the Unisar size of the abrasive particle is going to be less. So Unisar and then rhodite means generally they are going to be cerium oxide abrasive particles. Only the size is generally is going to be. So because the supplier is generally, they may named it as a rhodite and the Unisar. So because of that, we are also calling the same thing. So means nothing but, so whatever the induced dipole movement, which will be directly proportional to this diameter of the abrasive particle, so diameter of the CAP particle along with the magnetic field, applied magnetic field strength. So because of that, so when increasing the magnetizing current, yield stress is generally is going to be increasing in both the cases, as well as if you're in smaller abrasive particle size, or even for the larger abrasive size particles also. Only the thing is, depends upon the type of fluid we are going for, the type of when particle is going to be. So CS, which is generally is going to be magnetically soft material, so which is also the size of the CAP particle is also generally is going to be more, so which will be having the more yield stress compared to this two other things. So and this OS is generally can have because it is coated with the silicon dioxide coating, so generally it is experiencing the less yield stress compared to the other two. As well as we can see the even viscosity also. So viscosity, apparent viscosity is going to be increases with increasing the magnetic field, but not the case with respect to the where CAP OS, which is generally is going to be coated with the silicon dioxide. It is showing this like a kind of shear thinning fluid actually. So another for next is we gone for this. So once we, because CAP CS grade, which is a soft soft grade of iron abrasive part, means a soft grade of CAP particles we have taken, and then and also it is having that the diameters, average diameter is going to be almost a 6 to 7 average, and the size of the diameter is going to be. And we have taken a rhodite is one of the, as a Syria average we are taken, so which is contains 3 to 4 microns. So and then tried with if we're increasing the CAP and then CAP particle concentration of the CAP particles and abrasive particles, and increase the magnetic field, magnetizing current. So what will be the again rheological effects we have, try to done. So when the increasing the magnetization current with when the yield stress is increasing when compared to this, like when we have the smaller concentration to larger concentration, so more and more always generally is going to be giving the better. But some extent like some extent of if you are further increasing the concentration of the CAP particle, but yield stress is generally is going to be decreasing, because abrasive particles are going to be there, as well as CAP particles also generally are going to be there. So generally because of the more particle thing, movement is generally is going to be restricted to. So because of that, generally you can say yield stress is generally is going to be low for when you go for higher CAP concentration is going to be used for that. Even the same thing can be able to observe it in case of the viscosity also. As increasing the, we can take, as increasing the cerium oxide also, generally magnetic yield strength, yield stress is generally going to be reduced in these cases. And even we have seen this effect of like a CAP concentration, abrasive and magnetization current on the when you are going for polishing the this silicon. So the same thing can be able to observe it, like CAP, where increasing the CAP concentration, like where when iron particles increasing, so reduction in the surface roughness is going to be taking place, right? That is going to be correlated with this yield stress and then viscosity. Right, even magnetization current is increasing, generally we can have the even reduction in the surface roughness is going to be taking place. But beyond, I already told you, like if you are having the more concentration of the abrasive particles, and then CAP particles are generally are going to be there. So generally surface roughness is not generally having that much effect, is going to be much more, we are not able to observe that. Syria particles, abrasives are generally are increasing. So some up to almost 6 to 7%, this the reduction is going to be taking place. And after that, there is no use of using this higher amount of abrasive particles in the case of this when you are going for the polishing the silicon. Even the same thing almost most of the people are observed. So an optimum concentration of the CAP and abrasives are generally optimum concentration of the abrasives are generally are going to be 5 to 6%, whereas in concentration of the CAP is not more than the 30 to 35%. If we are able to, then mostly, I mean, like if you are carrying fluid is generally is going to be up to 60%, is always is going to be better, and remaining things we need to be restrict to the 40%. So in order to have, I mean, like polishing the surface, generally I have used this NaOH is also you have used like a kind of a surfactant, I mean additive in order to get the stabilizations and the dispersibility. So this is the same photograph which is going to be taken as the 16,000 magnification. So the silicon is going to be, and after finishing where you can get very 39.5 nanometers we achieved in case of while finishing the best one we observed. The same thing, like we also tried with the working gap, rotational speeds, and magnetizing currents. Just like a brief I just tell you. So if the working gap is going to be increasing, so automatically the strength is of the generally is going to be reduces. So generally we are getting the less very rough surfaces we are able to getting. So means nothing but we are not getting much more finishing. Even rotational speeds also. Rotational speeds up to 300 is okay. More than that, generally is not advisable to go for going for this polishing applications. So because of what I can say that I'm sorry, centrifugal force will come into action. So because of that, rotational speeds up to 300 RPM is generally is going to be advisable. As magnetizing current means it plays as magnetizing current is increasing, generally we can have the more and more surface finish can be able to achieve it using this thing. So that's what like lastly I just told you, like we even 457 nanometer surface finish, then from that we got 89.8 nanometer surface finish we achieved using this we're working gap on this. For this I have used some design of experiments I have used. Finally, these are the generally is going to be optimum level of process parameters. So from the optimum level we achieved this surface finish. So finally, coming to the conclusions. So these MR materials based products generally which are used in like maybe vehicle damper, utilizing this MR have been practically realized as a commercial product, right? Even some products introduced into in this general article in this presentation shows this innovative design concept to achieve the enhanced performances also. In order to accelerate this practical utilization of MR fluid devices and systems, several requirements need to be satisfied, right? So advanced material, MR material itself, like generally it is a very costly process actually in order to, and again CAP particles means like a highly purified form of iron particle. So that itself generally is going to be a very costly actually, and then getting into that particle sizes and then all those things also, it is not that easy task. So and the new design concepts and principles and optimal control strategies is going to be required durability in in several environment, that also you have to be taken into consideration. Like this generally can be able to operate only like minus 10 degrees to only 150 degrees centigrade only, just only this range only we can able to apply. Even less than that, and even above that we cannot be able to apply those things also you have to take it into consideration. And then field dependent rheology control characteristics of the materials very crucial, like to validate the benefits of this performance controllability. That already told you, the major is going to be stability is the one major important thing, like dispersion and redispersion is also another problems are going to be there. And then heat dissipation as generally are going to be bottlenecks, which will generally is limiting this application at present. Even there are a lot of products are there, commercial products are there, but generally it's not completely it's not coming into market. So this is a new type of intelligent material. So it has the excellent performance in the field of modern precision machining. Coming to the machining process, polishing process. So this has the processing has a irreplaceable advantages compared to this traditional polishing machining, and has widely used in the precision and ultra precision machining only. But when this MR polishing equipment also need to strengthen the Metallurgical polishing polishing research, like on the non-spherical surfaces, and then broaden the processing adaptability and improve this effectiveness, and reducing the processing cost also. Still, all these polishing just only QAD technologies is came into, and remaining things MRF polishing techniques are generally developed by academic people, not in the still in the research stage itself. So only few things are generally going to be commercialized, and a few still there need to be commercialized to go for. Even this commercialized one also generally are going to be very costly. The machines and other things also only it will be benefit only for some applications only, like polishing of glass and another thing only. And people have tried a lot of different materials like copper and fused silica, even some kind of dental materials also they have tried it. So, and still completely in case of still in the what you can say that research areas only, because the major problem is going to be while preparing this metallurgical polishing fluid. So, stability is one problem. Means once you just synthesize the part, MR fluid, and then keep it aside, for a few days afterwards, generally there becomes like a kind of cake in the bottom, and the fluid is generally going to be flows over that. So when again, so redispersion of these particles, again, it is very challenging task actually, even that. And then once we are preparing a water-based, generally water will be continuously, evaporation is going to be takes place. So again, you need to be refreshed, your need to be conditioning has to be done continuously. That is another challenge is has to be taken. So control over all those things is still, some of the bottlenecks are there. So maybe in future might be this is will be what you can say that go for and maybe completely it may come into the commercial aspects. Maybe people will synthesize own fluids and other things. And what are the research interests are generally are going to be there? One thing, synthesizing the MR fluid, MR polishing fluid for applications. One thing. Another thing is generally people are not tried with the modeling part. Even they tried with only very few journal papers are there only for modeling the aspects are like generally of MR finishing process. So that completely nobody are touched with that part. And then again, I told you synthesizing only up to laboratory way are generally people are doing, not way generally is going to be commercial way of doing. Only lot people are doing. That too only for MR fluids only. MR polishing fluid only QAD technologies are there developing. Any questions, other things?
Thank you, madam. Thank you. Thank you for the very effective and useful lecture, madam. Thank you.
Thank you, madam, for giving the opportunity.
Thank you, madam. Dear participant, any questions?
Lastly, I have rushed through fastly because of time lag.
But a lot of introduction you have given, madam, about MR fluids. Madam, one question. Ma'am, any solution for agglomeration problems in synthesizing of MR fluids?
So that's some of, we can use some kind of surfactants or otherwise based on the type of, MR fluid you are preparing, MR polishing fluid is preparing. Based on that, we can go ahead. Like for example, we used for glass and some kind of, when you wanted to finish the silicon. So water is generally is going to be used as a base fluid. For that, generally we can go for either NaOH or KOH kind of additives can be able to add it, so that generally they'll also act as a kind of, they'll limit the agglomeration problem. But generally this will be like many other applications, they use little oleic acid and other kind of surfactants, they use it for to reduce this agglomeration. And I'm telling that like a lot of technologies are completely, they have the patents and they'll prepare. I don't know how they'll prepare MR fluid. Just only, for we wanted to check the viscosity and other things also. So what we done, like we just, what are the damper, we purchased the damper and then entirely we'll take a note and then we extracted the fluid. And then we kept it for almost 1.5 months, 2 months also. But still, once you shake it, that the bottle, immediately the redispersion of MR particles are going to be taking place. But once we tried with in the synthesizing this MR fluids, but with the oils also, even silicone oils also, we tried it. but we never achieved that kind of things. Once you keep it for aside for months, in that cases, again, reciprocity is a major problem, is a major challenge actually. Even still, that problem is going to be existing in that. Might be they use this abrasive, the CAP particles, or might be they use it very smaller in size actually compared to this polishing. Polishing required little bit higher size of abrasive, this CAP particles. Other than the abrasive particles, even CAP particles are also generally is going to be a little bit larger in size. I hope, I think you understand this.
Dear participant, any more questions? You can unmute yourself and you can ask madam. Or if you want, you can type it in chat box also.
So when you add the surfactants, no, generally they'll coat on over the surface. So because of that, I mean, attraction force is going to be reduced between the particle to particle. So generally the agglomeration problems can be able to reduce it. But it depends upon the type of I mean, base fluid you are using. Based on that, you can go ahead.
Is this process restricted for some materials, madam, or any materials can use?
I mean, people have tried already. Copper, they have tried. Even in IIT Delhi, where I have worked with my guide. So myself, I have worked with the silicon. Right, another person, when he worked with some kind of stainless steels also, steels, and then copper, even glass materials he done. And one more person completely, he developed different type of more polishing fluid for copper, actually, only for copper. But right now, very widely used is for I mean, like kind of brittle materials where glass and kind of silicon actually used.
Okay, madam. Thank you, madam. Dear participants, any questions?
So might be they are hungry.
It's taking 1:30.
Hmm.
Thank you, madam.
Okay, ma'am. Thank you very much once again.
Effective and useful lecture, madam. Thank you so much.